Hi guys, and welcome to grade 11 Physical Science Learn Extra Live. My name is Indiana and tonight we're with Bruce. So I hope you guys haven't missed me too much, and that Ty's been doing a great job. I've been watching him from the back of studio and I like what I see. I like a lot. Guys, last week's lesson was our gas laws with Bruce, and tonight's topic is electrostatics, and I think Bruce is going to tell us a little bit more about it.
Yeah, thanks very much, Indy. Yeah, guys, we're going to start a new section of work tonight. We're going to be looking at electrostatics, basically the whole concept of charges at rest. And I'm going to be developing a couple of theories, looking at a few laws, and we're probably going to be doing the electrostatics for tonight and probably next week as well. But also one thing to remember, guys, if all the grade 11s who are watching last week, I said that we'll do a worked example. I'd give it to you guys this week as a challenge. So when we come back after the break, I'll talk a little bit about those gas laws, that example that I want you guys to do, and then we'll get right back into electrostatics.
Fantastic. And guys, next week will be electrostatics again. Hey, Bruce?
That's correct.
Yeah. So what I'm asking you guys to do is, if there's anything you are struggling with, please let us know and post it onto our page and be specific about it. And we will be asking your questions at the end of the lesson, the last 15 minutes. Don't forget to chat to us on facebook.com/learnextra. Also chat to us on Twitter @learnextra. While you're watching, shoot those questions in and we'll get ready. Well, we'll go through them in the last part of the show. I also have a Casio calculator to give away that we will be announcing the winners tomorrow on the page. I think what we're going to do is we're going to go to a quick break, and when we get back we'll get working with Bruce. See you then. Hi grade 11s, and welcome back. Finally it's your time, and I'm sure you're excited about the show. Grade 12s, I know you're tuning in too. Kashifa and Noxie always on the page, I see. Hope you guys haven't missed me too much. But without further ado, I think what we're going to do is we're going to go straight to working with Bruce. Don't forget to send questions in as we go along, guys. Okay? Bruce, take it away.
Indy, thanks very much indeed. And guys, welcome to the show. Really good to be back. We are going to be looking at a new section of work today. We're going to be looking at electrostatics. But as I said in the introduction, I promised you guys last week a question, or one of the last questions on the gas laws that I'd like you guys to actually try. So what we're going to do is that we're going to put the question up. We're going to look at the question, and then you guys are going to do it, or hopefully during the time that we're on air, and right at the end of the show, Indy, I think what we can do is just go back and I'll go through the answer, just make sure that everyone's got it right, and maybe the first person who can shoot Indy the correct answer through Facebook or through Twitter, that can be the person who's going to win the Casio calculator.
Fantastic.
How does that sound? I think that's probably a good way to do it.
Fantastic. Good.
Great.
Let's do that.
Okay, so guys, there it is up on the board. I'll give you a little bit of time to take it down. It says here carbon dioxide gas, remember the formula for carbon dioxide gas is CO2, is collected in a 20 cubic centimeter container at a pressure of 105 kilopascals and at a temperature of 20 degrees Celsius. What they want to know in this question is, what is the mass of carbon dioxide in the container? That's our question, our challenge for tonight, and hope you guys have got that down. As I said, do the question, shoot into the answer, and hopefully the first person will be able to get that beautiful Casio calculator, which we'll be announcing on Facebook, on the Facebook page tomorrow. That's great. Right guys, so while you are working with that, I'm going to move over and we're going to have a look now at our section on electrostatics. Okay, it's a physics section, okay, so it's part of our physics component of the physical science, and what we're going to be having a look at is trying to develop our basic understanding of electrostatics and making sure that the concepts that we learned last year in grade 10, and I'm sure you guys will probably remember this from grade 10, that those concepts are now cemented down, and that we can now move to a little bit of a higher level and start introducing a couple of new laws, a couple of new concepts, and we understand electrostatics just that little bit better. Okay, so what I've done at the moment is quickly looked at a bit of a recap from grade 10 level, just to make sure that we do understand exactly what we're talking about when it comes to electrostatics. So my first question that I put up here on the board is, what is electrostatics? And guys, if you have a look over here, you'll be able to see, let's get the pen out, that it's the study of charges at rest. Absolutely fundamental. We're looking at charged particles at rest. Now, from grade 10, you will also remember that there's also a study of where we look at charged particles that actually move. And I'm sure you guys are probably saying, well, I know the answer. Well, that answer is current electricity. When you looked at electrical current, that was the movement, or the study of charges that are moving through a conductor. Electrical current. Electrostatics. If we look at the name, electro, and there we get that part over here, static, which means stationary, and that's why we call it the study of charges at rest. Now let's just remind ourselves a little bit about what is a charge and how we actually develop our concept of charge. Well, the first thing we have a look at is that we must remember that all matter is made up of atoms. So we go right the way down to our basic building block of all matter. We go to the atom. Again, all stuff from grade 10, and just to reinforce that a little bit, atoms contain positive charges which are found in the nucleus, and we call those the protons. All revision from grade 10, and negative charges which orbit around the nucleus, which we call the electrons. And guys, very important to remember that when we're dealing with atoms, the overall charge of an atom is going to be neutral. So in other words, what we're trying to say now is that there are equal numbers of positive protons and negative electrons, or positive and negative charge in an atom. So guys, what is that basically trying to tell me? Well, it's basically trying to tell me that right down at the basic building block of all matter, okay, we've got the atom. The atom has got positively charged particles in the nucleus, the protons, negatively charged particles which are orbiting around the nucleus, the electrons. We've got two basic types of charges. We've got a positive charge and we've got a negative charge. So when we look at electrostatics, these charges at rest, we're going to be looking at positive charge at rest and negative charge at rest. And obviously the interactions between those charged particles, and we're going to develop it from there. Okay, right, a little bit more I've got over here. So there I've put it, I've summarized it for you. Thus, in nature we find two types, or have two types of charge, our positive charge and our negative charge. And again, to reinforce, is that when an object has an equal number of protons and electrons, it is electrically neutral. Okay, guys, I'm sure that was quite simple. Hopefully a few of you guys maybe just jotting a couple of notes down. Just make sure that you cement that knowledge, because we're going to take that knowledge going forward. Okay, right, let's move on to my next slide. Now, here's one of the big fundamental questions. How do objects become charged? Okay, how do I create a static electrical charge? Well, guys, one of the most important ways, and also the simplest way of doing it, is through the process of friction. Okay, we rub objects together, and whenever objects rub, we can actually create a charge on those particles. Now, when I say the word create, I don't mean we just suddenly develop. It doesn't come out of nowhere. There's a very important set of rules as to indicate to us how these particular substances become charged. It's through the process of friction. Okay, and we can either charge the object up positively, okay, and when we talk about a positively charged object, we talk about the object being electron deficient. And I just want to highlight that, underline it. We talk about the object being electron deficient, and that is a very important concept. Okay, the negatively charged object, well, now we don't talk about it being electron deficient, we talk about it having an excess of electrons. we have got more electrons, an oversupply of electrons. So can you see now, guys, that when we talk about positively charged objects and negatively charged objects, we look at the whole thing through the movement of electrons. Okay, either we are taking electrons away to make it electron deficient. Okay, so here we're taking electrons away from the object, okay, to make it deficient. Or if we're now making it a negatively charged object and we have an excess of electrons, we are adding electrons. We are adding electrons to the object. Now, that process of friction, okay, when we rub objects together, that is going to either cause electrons to be rubbed off, okay, to take them away, or electrons to be rubbed on, to add them to that object. Okay, we never, ever, ever talk about rubbing positive charge on or positive charge off. Okay, and maybe another little challenge, India, I can throw out there is maybe on Facebook or Twitter, and we can answer this a bit later, is why we never actually want to, or why we never can rub positive charge on or positive charge off. So maybe that's
Fantastic.
something else. Let's see if anyone comes back to you on Facebook and Twitter on that one.
Fantastic.
Okay, cool. Right, now, here we go. So, I'm going to quickly show you exactly how this is going to work. So, if I want to charge an object up positively, what I've got here is a sort of a rod. I've got a rod, an object that I'm going to try and charge. And what I've put here is alternating positives and negatives, which I'm trying to indicate there that this rod, before I do anything with it, is going to be electrically neutral. Okay. Now, what I'm going to do is that I'm going to rub it. So I'm going to rub it, and there's a surface, and we're going to rub this object on the surface. Now, if I'm going to charge it up positively, remember what I just said? We have to now rub electrons off. We take electrons away from that object. So what I'm showing over here is electrons now are being removed from that object due to the process of friction. Okay, and I've put over here, the rod is rubbed on the surface and electrons are rubbed off the rod. Now, if electrons are rubbed off the rod, can we see now that we have got positive charge left behind? Positive charge does not move. Therefore, if electrons are rubbed off, we have got an excess, or should I, sorry, let's put it this way, a deficiency of electrons. We can see now our deficiency of electrons, and therefore our rod is left with an overall positive charge. And that is how we now charge the rod up positively. Okay. Now, an example of what type of object will actually charge up positively, well, a perspex rod will do that. Now, guys, perspex is just simply a type of plastic. A lot of you guys have got perspex rods at school. In fact, we don't call them a perspex rod, you guys call it a ruler. And a ruler generally is made from a substance called perspex. And therefore, and as we approach the very dry winter months, a lot of you guys sort of take your rulers and you rub them on your jerseys and things like that, and suddenly you find it starts picking up little pieces of paper, and even if you hold it next to your hair starts to stand on end. That's all because of static electricity. Okay. And we mustn't also forget that our wonderful fireworks shows that we have in summer, through our lightning storms and things like that, again, fantastic static electricity type theory that goes on in the clouds themselves. And that sort of stuff that you probably have looked at in grade 10. Okay, but let's move on, and let's have a look now at our negatively charged rod. Okay, how do we charge this object up negatively? So once again, there I start now with my neutral rod, with positives and negatives balancing each other out, so that the whole rod is actually neutral. And what we now do is we also rub this rod, so we rub it, okay. All right, what's going to happen? Well, in this case, we can rub electrons on. This is the other option. We can have the ability to rub electrons onto the rod. So can you see now that by doing that, we must create an excess of electrons on the rod. You're going to have more negatives than positives. And if you have more negatives than positives, then surely the rod must become negatively charged. And that's what we put over here. The rod is rubbed on the surface, there's our friction, electrons are rubbed onto the rod. We are adding electrons to create an excess of electrons on the rod itself. So therefore we can now show the rod having an overall negative charge. And there it is, its excess of electrons, overall negative. Give another example of this. Well, a nice example is a PVC object, okay? And a PVC is also a type of plastic. PVC stands for polyvinyl chloride. You find a lot of that in rubber piping and stuff like that. PVC has the ability, when subjected to friction, to actually have electrons rubbed onto it. So PVC actually charges up statically as a negatively charged rod. And that, guys, basically gives us the overall introduction as to how we can charge rods up. And we're talking about static electricity, and now we're talking about a positively charged object, a negatively charged object. And what we're now going to have a look at is going to be how these charges now interact with each other. What happens when I bring a positive rod closer together, close to each other? What happens if I bring a negative rod close together, two negative rods close together? What happens if I bring a positive and a negative close together? And I'm hoping that next week I'll actually be able to show you, because I'll try and get these rods and I'll try and get them nice and nice dry atmosphere. We can charge them up, and guess what? We should be able to reinforce some of the theory that we're doing today. Okay. Any questions have come through at this stage?
We've got a few questions, but let me have a look here. Sini Temba wrote back to your question.
Okay.
Can I read? I think it's to him. His question out to you. Okay. So to answer Bruce's question, we can't rub off protons because they are situated in the nucleus of atoms, meaning a lot of energy would be needed to remove this proton. Electrons are rubbed off easily. Good answer?
That is it. Indeed, the question came to how quick did it take for that question to get answered?
It was done 3 minutes ago, so,
right, so
yeah,
pretty much in the last couple of minutes. Guys, that's exactly correct. The answer to my little challenge there was that why are we only talking about movement of electrons and not movement of protons? Well, protons are fixed in the nucleus of the atom. Excuse me. So therefore, the protons cannot move. The protons are held in that nucleus. The electrons are orbiting around. The electrons are moving. They labor. They've got energy. Therefore, they can be rubbed off. They can jump off away from the atom. Okay, those protons are held in the actual nucleus. Great answer. Fantastic answer there.
Okay, Caesar wants to know what is electron deficiency?
Sorry?
Electron deficiency?
What is electron deficiency?
Yes.
Okay, electron deficiency is a lack of electrons. Ooh, sorry, my throat's going in a little bit. It's a lack of electrons. In other words, if you are short of electrons, then you say that you are electron deficient. If you've got more electrons than you actually need, then you've got electron excess. Okay,
Fantastic.
So electron deficiency, a lack of electrons, electron excess, you've got more than enough.
Okay, fantastic. Okay. I think what we're going to do, guys, is we're going to take a little break, give Bruce a little time to get some water and have a little cough. Shame. You do the same, guys. Make yourself a cup of tea, get yourself a glass of water. Get those questions in on the page, facebook.com/learnextra. Also chat to me, Indiana, on Twitter @learnextra. I'm here to help you get those questions answered. And remember, there's no such thing as a silly question. We'll see you now after the break. Hi guys, and welcome back to Learn Extra Live. This is grade 11 physics, and we're all having an awesome time. Guys, don't forget to get those questions in on the page. Please make sure that you show us where you're not understanding, and don't forget that we'll be taking the questions in the last 15 minutes of Bruce's show, so get them in good and early. Another thing I want to say is thanks so much to Liberty for making this possible. You guys absolutely rock. And before we forget, we also have this calculator that we're going to be giving away on the page tomorrow during the lesson. So get your questions in, and don't forget this one. In this specific show, we're giving away the calculator to Bruce's challenge question. So whoever gets this right first gets the calculator. I'm going to repost the question, and I think we're going to go straight to Bruce and get those answers coming in. Bruce, take it away.
All right, Indy, thanks very much. And guys, welcome back after the break. As I said to you guys, we've now looked at our how we establish our static charges, our positive and negative. I just want to quickly show you how we represent these charges, and then we're going to have a look at our first fundamental law of electrostatics, and we're going to introduce what is called Coulomb's law, but I'll talk to you a little bit about that in a couple of secs. But guys, what I'll quickly want to do is, we often, when we represent a charged particle, especially when we talk about electrostatics, we often just represent it as a round circle with the charge of that object illustrated in it. So what I've got here is a little circle, and I've just put a positive in there. That tells me now that I am measuring a positively charged object, or I'm dealing with a positively charged object. If I had a negatively charged object, I would simply write it in like that. That represents a negatively charged object. Okay. Now, what we are going to have a look at, and I'm going to stay with this at the moment, is we've got our two charges. What happens if I have a positive and a positive brought into proximity with each other? What happens if I have a positive and a negative charge brought into proximity with each other? Or what happens if I have a negative and a negative charge brought into proximity with each other? Now, a lot of you guys will probably say, well, isn't it very similar to magnets, where magnets use north poles and south poles? Well, guys, yes, it is. It's very similar in terms of the effect that's going to happen. So if I say to you guys, if I have a north pole of a magnet and a north pole of a magnet, you guys are going to turn around and tell me, are they going to repel each other? And if I have a north pole and a south pole, then they're going to attract. And if I have a south pole and a south pole, well, they're going to repel each other as well. So guys, we have a very similar type of situation when we bring two charged objects into proximity with each other. We either have, and I'll just extend the page a little bit, we can either have attraction, okay, whoopsie, or we have repulsion. Okay, and the important thing, guys, is that these are all forces. Okay, we talk about forces of attraction and we talk about forces of repulsion. Okay, and just like with magnets, where we had like poles were repelling and unlike poles are attracting, we get exactly the same thing over here. We get our like poles, which we say like charges, okay, and they are going to repel, okay, and we have unlike charges, okay, and they're going to attract. So, if I just go back up slightly, and I'll put down my representations of my charges, and I'm going to change the color, and I always like that color, so I'm going to have a bash at it. Negative and negative are going to be like charges. We're going to get repulsion over there. Positive and positive, also like charges, we're going to also get repulsion. And positive and negative, well, there we're going to get our attraction. Okay, so guys, just as a quick little leader into my next section, we've now just looked at quickly representing our charges and quickly what happens when we have different charges in proximity or brought close to each other. So, what I'm going to do is just go back to my original notes, and I'm just going to go back over here, and I'm going to find my notes over there. And there we go. We are going to now look a bit more specifically and a bit more detail at the concept of what happens when we study the force between charges. And this is known as, and now I'm going to go back to my green, it's known as Coulomb's law. Okay. Now, Just a little preamble and to bring it in there. Our like charges repel while unlike charges attract. And these are known as electrostatic forces. So this force of attraction or repulsion are called electrostatic forces. Now guys, you've probably done some forces already and you've heard about gravitational forces and magnetic forces and frictional forces and things like that. If we're dealing with charges, we talk about electrostatic forces. And this is what was studied, and in fact, if you have a look at the date, it's quite a long time ago, 1784, okay? Charles Coulomb, he was a French scientist. In 1784, he actually investigated the whole concept of forces between charge. And what did he find? He found that the force between the charges increased as the charge size increased. In other words, as the charge got bigger and bigger, there was a bigger charge on the object, so that force started to increase. However, when the distance between the charges became smaller, he also found that the force was going to increase. So there were two things he was able to establish. That to increase the force between those objects, you could make the charges, the actual charges of the objects bigger, as well as make the distance between those charged particles or charged objects smaller. And he came up with a proportionality. He came up with a mathematical mathematical proportionality. And he said that that force is directly proportional to the product of the two charges. Now, you can see now we introduce the symbol for charge, which is given by the symbol Q, and that represents charge. Okay, that's our symbol for charge, Q. Okay, so if we've got two charges, let's call the one charge Q1 and the other charge Q2. We simply multiply the two, okay, and then as the distance became smaller, okay, so the force got bigger, we have an inverse proportionality. Therefore, he had to divide, but the important thing is he divided by the square of the distance between those charges. So guys, Charles Coulomb came up with a very, very clever and very, very significant equation that allowed scientists now to measure and calculate this amount of force. And it can be either attraction or repulsion. It doesn't matter. That the force was directly proportional to the product of the two charges and inversely proportional to the square of the distance between them. And that's how he set up his equation. Now, let's just have a look at this in a bit more detail. Because it was so important, Charles Coulomb was honored with this discovery in 1784 by having this whole thing known as Coulomb's law. Okay, and this, guys, is one of the important definitions that you will end up getting tested on at some stage in your school career. State Coulomb's law. And here it is, guys. The magnitude of the electrostatic force between two charges is directly proportional to the product of their charges and inversely proportional to the square of the distance between those charges. Guys, that is Coulomb's law, and I'm going to make a little star over here to say, guys, please make sure that you learn that definition. If you've got a textbook or you're using notes at your schools, please highlight it, put a big block around it. You're more than likely going to get asked that in your next test when it comes to electrostatics. Okay, but now we've got Coulomb's law. We've got this relationship, a direct proportionality, the electrostatic force directly proportional to the product of the two charges and inversely proportional to the square of the distance between those charges. How do we now mathematically interpret this? Well, Coulomb's law now gets mathematically interpreted by having a look at this equation over here. We now replace the proportionality sign with an equal sign, but we have to introduce our constant of proportionality. And this is known as the electrostatic constant. I'll just write that here. The electrostatic constant. Okay. Or sometimes they do call it Coulomb's constant. But you'll probably find that most textbooks are going to be talking about the electrostatic constant. We give it the value of K, and it is equal to 9 times 10 to the 9 Newton per square meter per Coulomb. And that, guys, is a constant that applies to all electrostatic charges. If we're trying to determine that force, then we introduce that constant over there, and now we've got a mathematical equation that's going to allow us to calculate the magnitude of that force. So let's move on to that, onto a worked example, and let's go and have a look. Okay? Well, a very simple example that I've taken. I've said 2-point charges, just two charged objects. Okay? One has got a charge of plus 3 times 10 to the minus 19 coulombs, and the other one has got a charge of minus 5 times 10 to the minus 19 coulombs, respectively, are placed 2 meters apart from each other. Calculate the magnitude of the electrostatic force that will exist between them. Now, guys, before we go diving into this problem, just a couple of things I want to chat about before we move on, and that is now having a look at the two charges. Whoops, I see it there, and I want to just circle that little symbol over there. Here we have the unit of charge. Okay, now guys, let's be just very careful. We know that the symbol for charge is equal to Q, but we've got to measure Q in something. Well, we measure Q in coulombs. Okay, again, named after Charles Coulomb. Okay, who actually developed all this, and again, one of those things that they do with scientists, they honor them and they make great discoveries, and they actually honor them by giving him the unit of charge. So guys, we measure, or should we rather say, we represent our charge as Q, and we measure charge in the unit called the Coulomb. Okay, so we can write it out now. Plus 3 times 10 to the minus 9 coulombs, minus 5 times 10 to the minus 9 coulombs, and we have to calculate the magnitude of that charge. So guys, the magnitude of the electrostatic force between those charges. So guys, what is our first step? Well guys, I always encourage everyone to write down the information that we've got step by step from the problem. So they've given us our first charge Q. Q1 is going to be plus 3 times 10 to the minus 9 coulombs. Q2 is going to be minus 5 times 10 to the minus 9 coulombs. R, the distance of separation, is 2 meters. And K, our electrostatic constant, always going to remain constant at 9 times 10 to the 9 Newton per square meter per Coulomb. And there we go. Right, so all we have to do is substitute in. Very simple. Let's just substitute in the values. Please, guys, don't forget it's R squared. And a lot of people sort of, when they're rushing a bit, forget that it's R squared, and they simply put down the value of R, that distance of separation, without squaring it in the equation. Once we do that, there we go. We have now got an answer of 3,37 times 10 to the minus 8 newtons. And there's one little thing that's been left out, and that is it would have come out to be a negative value. Now, can you see why it's going to be a negative? Because we've got a minus 5 and a plus 3. And whenever we have a positive multiplied by a negative, we are going to get a negative value. So what does that negative value actually represent? Well, obviously, it's got a positive and a negative. We've got unlike charges. That represents attraction. Okay. So guys, what we must do, when we finish it off, we must interpret that negative sign by simply saying that it's an attractive force. Okay? Well guys, that's a nice simple little problem. Any questions that have come in while I've been talking here?
Okay, there are quite a few. Guys, don't be afraid. If you do have any more, please send them through. Princess has said, are we going to be given K on the information
Correct.
sheet?
K is given on the information sheet in all tests and all exams. No problem, don't sweat about that.
Okay, so guys, I see that there are a few answers coming through for Bruce's challenge. We will be going through it at some point, and we will be announcing the winner at the end of the show. So guys, you just keep stuck to your seats there. Okay, Ebenezer wants to know, why do we use micro coulombs and nano coulombs instead of coulombs to measure charges?
Okay. Right. In fact, that's just led me into my next little
fantastic.
topic. So that was a
Ebenezer.
great question, because that's led me beautifully into my next topic. I want to talk a little bit about this unit of the Coulomb. Okay. Now, as I said earlier, we measure charge in coulombs. But one thing we're going to have to take into consideration is that charge can be incredibly small. You might say, well, hang on, but what about lightning? Lightning is a big electrostatic bolt. It's a discharge of electrical energy. Sure, that's big. But if we're dealing with small little objects, especially little objects that you're rubbing on your sleeve to charge up through friction, those charges actually are very small. So what I want to quickly have a look at is what is called orders of magnitude of charge. And I'm going to bring up a blank sheet, which I put in over here. All right. And we're going to talk about magnitude of charge. Okay. Now, can we just extend the page a little bit? Here we go. Guys, our magnitude of charge is, because charge is so small, we talk about charge in a couple of orders of magnitude. We talk about things called millicoulombs. We talk about charge in terms of microcoulombs. We talk about charge in terms of nanocoulombs. And we talk about charge in terms of picocoulombs. Okay, now I've got a feeling that everyone's now sitting on the edge of their seat saying, my goodness, what is all this coming all about? Well, what it's all about, guys, is that it's a very simple way of representing charge. And we don't have to write down all these big numbers that we've actually got. Remember, guys, I've just said earlier, charge can be very, very small. So therefore, instead of trying to write down like a fraction of a charge and lots of decimals and things like that, we actually are able to work out these orders of magnitude. A millicoulomb, okay, is a thousandth of a coulomb. Okay? 1,000th of a coulomb is a millicoulomb. A microcoulomb is a millionth. Okay? It's a millionth of a coulomb. So you can see now we're getting quite small. In fact, I'm probably going to run out of a bit of space here. So I'm just going to make some space available. A nanocoulomb is a billionth. Okay, a billionth of a coulomb. All right? And a picocoulomb is a trillionth. And another, there we go. Not unlike my bank balance at home, huh? No, not really. Okay, a picocoulomb is a trillionth of a coulomb. So guys, you might say, wow, but you said this, you make it simpler. Now you're introducing these even bigger numbers. Well, guys, what we do is that we introduce our orders of magnitude in a scientific notation. So if we talk about, and I'm going to change the pen color so it stands out nicely. If we talk about a millicoulomb, which is a thousandth of a coulomb, what we talk about is the symbol MC. A millicoulomb is given with a small m and a capital C. And we represent it as 10, whoops, I'm going to just do this like this, I think. We represent it as 10 to the minus 3 of a coulomb. That represents a thousandth. 10 to the minus 3 is 1,000th of a coulomb. Okay, I think I'm going to just use this pen. I think this one's a nice color. Now we talk about a microcoulomb. And a microcoulomb has got a funny little symbol. It's got like this U with a long tail. Okay, that is taken from one of the Greek letters, and it's used to represent a microcoulomb, which is 1 millionth of a Coulomb. And that is given to us as 10 to the minus 6 of a Coulomb. Okay. Now we go to a nano Coulomb, and we put a small lowercase n in front of the Coulomb, n with a capital C, which is a nano Coulomb. It's 1 billionth, and that's 10 to the minus 9 of a Coulomb. And then the last one is the picocoulomb, which is the trillionth, and we put a small p. In fact, let me just make that a little bit clearer, because it must be a small p. There we go. And that's called a picocoulomb, and that's given to us as 10 to the minus 12. And that's how we represent it. 1,000th, 1 billionth, 1 billionth, 1 trillionth. 10 to the minus 3 of a Coulomb, 10 to the minus 6 of a Coulomb, 10 to the minus 9 of a Coulomb, 10 to the minus 12 of a Coulomb. Okay. And what we can now do is, whoops, let's get this up. We can talk about, as an example, okay, we can talk about a plus 3,7 nanocoulomb charge. Now, if we talk about a 3,7 nanocoulomb charge, what that means is that its charge is 3,7 times 10. Now, let's bring it up a little bit. Remember, nanocoulomb was 10 to the minus 9, so therefore that represents 3,7 times 10 to the minus 9 of a Coulomb. Okay, one more quick example over here. Okay, let's call that example A. Example B, we can talk about 7,8 picocoulombs. Okay, and I'm going to put a negative there. So it's a negative charge, which means it's going to be electrons, it's going to be excess of electrons. All right. Minus 7,8 picocoulombs works out to be minus 7,8 times 10 to the minus, pico is minus 12 of a Coulomb. Okay, so guys, can you see now that what we can do, what teachers can do, what scientists can do, is that instead of talking about 3,7 times 10 to the minus 9 coulombs, 7,8 times 10 to the minus 12 coulombs, we can talk about 3,7 nanocoulombs, we can talk about 7,8 picocoulombs. And it just makes life a lot easier. And that's something, guys, that I hope you guys are going to remember, because you're probably going to see it come up in your questions. And I think I've actually got an example that uses some of these orders of magnitude over here.
Fantastic.
So that, I think, does answer that question quite nicely.
Fantastic. I think what we're going to do, guys, is we're going to take a break. And while we are taking a break, please don't forget to post questions on the page. Also, if you go into the page and you see somebody's posted a question that you understand, please go and answer it. And we like to, sharing is caring, and we're learning together. We're a team mindset. So what we're going to do now, take a quick break, and we'll see you right back then. See you now. Hi guys, and welcome back to the last 10 minutes of Learn Extra Live Grade 11 Physics. So guys, get your questions in, because we only have 10 minutes left of the show, and the better the questions, the quicker we can move through them with Bruce. So what I'm going to do is I'm going to hand over to Bruce, and we're going to leave the last 5 minutes open for that challenge question. So Bruce, since we're cutting it fine, I think take it away.
Right, thanks Indy. Well guys, as I said, we're going to now practice looking at Coulomb's law. We're going to practice looking at the new orders of magnitude of our charge, and I'm going to do another worked example with you guys, which is going to be fairly similar, but it does have a couple of little twists in it, and we're just going to have to be quite careful as to how we handle it here. So what I've got here is two charges, one with a charge of plus 4 picocoulombs, so now I've introduced my order of magnitude into the question, and the other a charge of 2,4 picocoulombs, okay? And they touch each other and are then separated by a distance of 0,115 meters, okay? Calculate the electrostatic force between these two charges, okay? So guys, we've got two charges. They're going to touch and they're going to separate out to a distance of 0,115 meters. Guys, how do we handle this type of problem? Well, first thing we've got to do, guys, is realize that when two charges touch, there's going to be an exchange of electrons, okay? But you might say, but hang on, they're both positive, so they don't have any electrons. Well, they do have electrons, but remember they're electron deficient. Doesn't mean that the electrons have disappeared. So the one does have slightly more electrons than the other, although they are deficient and there's an excess of positive charge. So what we do is when they touch, we get what is called an equilibrization or a balancing of the electrons out between the two charges. So how do we now work out the new charges on those objects or on those spheres or on those point charges once they touch? It's a very simple calculation, and I'll do it with you. All we do is we take Q1, okay, and that's 4,5 picocoulombs, and we've got Q2, which is equal to 2,4 picocoulombs, and I've just got the answers over here, so I'll just make sure I've got them with me. All we do is we say now that Q, which is going to be the charge on each one after they've touched, so I'm just going to put here Q touch, is simply going to be the sum of 4,5 picocoulombs plus 2,4, but we have to divide it by 2, because remember guys that you've got two charges and therefore the charges are going to be spread out between both of them, and they will therefore both be equal. So 4,5 plus 2,4 and divided by 2, and that comes out to be 3, and plus 3,45 picocoulombs each. And that's going to be Q1 and Q2. Okay, so the two charges have both now got exactly the same amount of charge. Once we know that, okay, we are able now, and I'm just going to go to a blank page over here. Once we know what the charge is, and it's Q1 is equal now to, and Q2 are both equal to 3,45 picocoulombs, we now know that the distance of separation R is 0,115 meters. We know that K is always going to be our constant of 9 times 10 to the 9 Newton per meter squared per coulomb. We are now able to work out the force between them. Okay, extend the page slightly. Here we go. We know that F is equal to K, Q1, Q2 over R squared. Now, 9 times 10 to the 9 multiplied by, okay, so we now got Q1 and Q2. Now, this is where we have to do and have a very important perception check. Although we are measuring, we've spoken about this in picocoulombs, we cannot use picocoulombs in the actual mathematical equation. We must convert that into coulombs. So what's going to happen now is that the 3,45 picocoulombs is going to now be converted into 3,45 times 10 to the minus 12 coulombs. And therefore, that now gets substituted in. 3,45 times 10 to the minus 12, multiplied again by 3,45 times 10 to the minus 12, because remember, we've got both charges, divided by 0,115 all squared. There we now have, extended a bit, there we now have our mathematics, and all we have to do now is plug that into the calculator, and we end up with an answer of 8,1 times 10 to the minus 12 newtons. Okay, so guys, quick recap of the question. If you have charges that touch and then separate again, we must work out the average of the two charges. Okay, simply add them together, divide by 2. Make sure that we've got the charges in the correct unit, which is coulombs, and then simply plug it in and work your formula. And it's as simple and it's as simple as easy as that. Okay.
Fantastic, Bruce. Okay, what we're going to do now, I think, is move on to the challenge question, since we only have 4 minutes left.
Wow, okay.
So, let's get straight to that.
Let's go to the challenge question.
Guys, I know a few of you have answered the question. I've seen 1 or 2 that are close, Bruce.
Okay.
So, yeah, let's get going.
Let's have a look. Right, there was our question. And here now is going to be the answer. Okay guys, remember from last week when we spoke about our gas laws, we spoke about our units of pressure and our units of volume. We must convert our pressure into pascals, and we must convert our volume into cubic meters. Right, 105 kilopascals is 105,000 pascals. 20 cubic centimeters, convert it, we divide by 1,000,000, and we get 0,00002 cubic meters as my volume of the gas. We've got R as our constant, we've got our temperature, converting it into Kelvin, 293 Kelvin, and here's our equation, the ideal gas equation. PV equals nRT. Why do I use that equation? Because I'm looking for N. If we're looking for an amount, we must be talking about moles, guys. So N will then be PV over RT. We simply plug in our information, our data, 105,000 multiplied by 0,00002 divided by 8,31 times the temperature in Kelvin. And there is our first step, is that we get the number of mole of carbon dioxide, which works out to be 0,00086 mole of carbon dioxide. Now, they're asking you, remember what they asked us? What mass of carbon dioxide is actually required? Well, then we use our very simple mole formula, mass over molar mass. There's the molar mass of carbon dioxide, 44 grams per mole. We rearrange, the mass is equal to the number of moles multiplied by the molar mass, 0,00086 times 44, and my answer comes out to be 0,038 grams of carbon dioxide is present. Indeed, did we get some winners?
Okay, guys, it's okay. You know what? There's no such wrong. Okay, there is a wrong answer, but that's fine. It's all about learning. Guys, if you got the wrong answer, hopefully you've learned how to get the right answer. If you haven't, please let us know where you've gotten stuck, and we will help you to do more of these in the future. Bruce, I was wondering, Makosi, he said 0,0396 grams of CO2.
Okay, there might well be, and this is what often happens, is that when the use of calculators, is that when they use the whole number, sometimes people round off a little bit too early, sometimes people don't. There can be a small discrepancy as a result of that. So how close was his answer?
0,0396 grams.
Okay, that was probably through rounding off. I'd say he's probably got it.
Yeah, I think so too.
He's certainly got it, sounds like it. It's just a rounding off.
Okay, cool. So guys, Mahosi, this one's yours. Please watch the page. I will let you know how to claim your prize. Thank you so much, Grade 11s, for such a fantastic show. Grade 12s, don't forget, you're on next with Phil. For today, that's me, Indiana. I have to say goodbye. Ty's on with you next, but keep learning more, keep learning extra. See you same time, same place next week. Bye.